Hello, this is Mr. Huber. In this lesson, we're going to look at arithmetic series. A little different than a sequence. Sequence is a listing of numbers. A series is the sum of those numbers. Okay, so a series is the sum of all the terms of a sequence. So we have a list that makes up a sequence. We add them all together. That's called a series. A finite series means it has an end. Okay, an infinite series goes on forever. Just so you think of infinity, goes on forever. So it continues without an end. So a finite sequence and then series, right? The sequence is the listing of numbers. The series is the addition of those numbers. Sequence, infinite, it keeps going on and on. Infinite, right? We'd keep adding it and add on the end of here. So we could keep adding on to the end of this as well. And we keep adding on there past 22. Okay, these are arithmetic. You can see the first one's adding 2 every time. Second one's adding 5 every time to get the next number in the sequence. So we got a series. It's the sum of those terms that we have in a sequence. How can we find the sum? Okay, well, there's a way we can find the sum of any finite arithmetic series. So any series that has an ending, we can find its sum by this equation that we see here. And it's important to note what the different parts of this indicate. N is the number of terms. Okay, N is the number of terms. So if we're taking a sum of 30 terms, this would be a 30. It means there N is a 30. So how many numbers we're adding together? That's the N, the number of terms that we're adding together. Okay, over 2 times, and in parentheses, the first term plus the last term, right? A sub 1 is the first term, A sub n is the last term. Right? If we're finding the sum of 30 terms, then A sub 30 would be the final term in that sequence. So we add the first and the last and multiply that by the number of terms over 2. This is an important equation to know that helps us find the sum for any finite series. So let's see how we can do that. If we want to find the sum of this series, yes, you could just add 3 plus 7 plus 11 plus 15 and so on, and you get it. We want to use that equation there because there's going to be times where it's going to be a lot easier to do that than just add up, these terms that we have here. Okay, so there are in this 1, 2, 3, 4, 5, 6, 7, 8 terms, right? 8 terms that we're adding up here. So to find this sum, we're going to the sum of these 8 terms is equal to 8 over 2, n over 2, times the sum of the first and last terms. So that equals 4 times 34, which is 136. So that'd be the sum of that series. Okay, the sum of that series would be 136. Okay? So you're saying, yeah, I could just type in 3 plus 7 plus 11. Yeah, you could. What about this next one? The sum of the even integers from 2 to 100. The sum of the even integers from 2 to 100. So you could sit there 2 plus 4 plus 6 plus 8. That's going to take a long time to add all the way up to 100. Imagine if we went past 100. So here, we could find the sum of this. There's 50 terms, right? Even numbers from 2 to 100. So that's going to be 50 over 2 times 2 plus 100. The first term is 2, the last term is 100. So 25 times 102, that comes out to 2,550. That would be the sum of all the even integers from 2 to 100, 2,550. So that's a relatively direct and quicker method to get that sum rather than just add over and over and over and over again, all the way from 2 to 4 to 6, all the way up to 100. Okay? So let's see a couple other examples here where we're going to be able to use something called summation notation. Okay? It's a different way of writing out a sum. Okay? We use the Greek letter sigma, which is this, right? Looks kind of like a big E, if you will. All right, that's the Greek letter sigma. Sigma, sum, okay? And when we're taking sigma notation, this is telling us that we're going from n equals 3 to n equals 108. These are the numbers we'd be plugging into this to get the sum, how many terms there are, okay? This is the smallest integer we'd put in there, and this is the biggest integer we'd put in there. So if we were going to find this sum, this indicates sum. This means we're trying to find a sum, adding up a bunch of integers, okay? So we'd plug in a 3, then we'd plug in a 4, then we'd plug in a 5, then we'd plug in a 6. It goes on forever, right? We don't necessarily want to do that. That's where we're going to use that summation equation that we just used before. We're going to be able to use that in instances like this as well. We need to recognize this indicates a sum, okay? And these are the lowest value we plug in and the greatest value we plug in, okay? If this is an infinite series, in an infinite series, we would take infinity and put it up here where the 108 is. That would be indicating this goes on forever and never ends. This is going from 3 to 108. It has a finite ending, okay? And the number of terms we have here, we subtract 108 minus 3 and then add 1. Okay, 108 minus 3 is 105 plus 1, 106. There's 106 terms in this series. So when we're taking that summation notation, okay, and we're trying to use it to find the actual sum, right, we go back to what we did before here, right? The number of terms is important. So how do we find the number of terms to put in here, right? We can take those two values above and below the summation notation, and we can subtract and then add 1. Right, so let's keep that in mind, and we're going to see here where we can use summation notation, understand it, and find actual sums. Okay? So what's the summation notation for the series below? Here we're just trying to write out the summation notation. Okay? So in order to write that out, we need to know the lowest and highest values we're going to plug in. So we need to know the terms that we're going to be using. Okay? And we need to have some kind of an equation that we could use for this. Okay? So we're going to talk about those two things. First, the number of terms. Okay? So to start this, we're going to figure out the common difference. We can see that the common difference is 4. Right? We're adding 4 each time. So that's our common difference. So we can use that to find the number of terms. So our final term in this is 207. That's going to equal the first term plus n minus 1 times the common difference. This is from our arithmetic sequences lesson, right? A sub n equals a sub 1 plus n minus 1 times d, right? And then that's how we get this. A sub n, so the 207th term, the last one, we're going to try and figure out what that n is, equals 7, the first term, plus n minus 1 times d. Now we can solve this equation. We can subtract 7 on both sides and get 200 equals n minus 1 times 4. Then we divide both sides by 4 to cancel out there. All right, divide by 4. And we get 50 equals n minus 1. We add 1 onto both sides, and we have n equals 51. So now we know the n. We know the number of terms. So we can write our summation notation. Summation notation, we're going to go from n equals 1 to 51. And our equation that we're going to write here, we want to use the common difference as basically our slope, right? 4n. That's the number we're adding repeatedly, okay? And then what we want to do to figure out the rest of this explicit formula, right? This is our explicit formula when we talk about arithmetic sequences. And now we're putting it into a series. If we take a 1 and plug it in here, 4 times 1 is 4. Our first term needs to be a 7. So we need to add 3 more onto this. We need to add 3 more onto this. So this is our common difference. The common difference right here. N is our variable, 4n. Then how do we get the plus 3? We'll take a 1 and plug it in here. If we just did 4 times 1, we'd have 4. But we don't want our first term to be 4. We want it to be 7. So we need to add this 3 on. We can try for a different term. Let's try the third term. Right? We will want the third term to be 15. So if I take a 3 and plug it in here, 4 times 3 is 12, plus 3 is 15. Right? We can see this is going to work to give us these terms in our series. Okay? So this would be the summation notation for that particular problem. That would be our answer. What is the summation notation? Summation notation is written right there. That sigma sign, right? Again, this is our sigma notation. We're going from 1 to 51. We got the 51 by solving for how many terms there were. We don't know. There's a big list. How do we know how many terms there are to get to 207? We had to figure that out. Okay? And then our explicit formula definition right there. So we're going to try another one. You should try this. Let's see if you're on the right track to figuring it out. It might be good, too, to see if you get the number of terms part right, and then see if you can write it as sigma notation. So pause it, do a step, play it, and see if you're on the right track as you're going. Okay, so let's see if you've figured out this a little bit and on the right track. So our common difference is 3. That'd be our first thing we need to figure out, that our common difference is 3. Okay. Now we need to figure out the n, the number of terms. So we're going to take 245 equals a sub 1 plus n minus 1 times the common difference. We're going to subtract 2 on both sides. So when I subtract 2 on both sides of this equation, I'm going to get 243 equals n minus 1 times 3. Then I'm going to divide by 3 on both sides. 243 divided by 3 is 81 equals n minus 1. And so when I add 1 to both sides, I'm going to n equals 82. N equals 82. And so now I can use summation notation. N equals 1 up to 82. Okay. My common difference times n, so 3n. And then again, if we look at, plug a 1 in here, 3 times 1 is 3, but we want to have a 2, so we need to subtract 1 more from that. So I'm going to subtract 1. This would be our summation notation. Okay. See if you want to see if it works, okay, let's find this term right here. This would be term 81. This would be a sub 81. So that means I'd take an 81 and plug it in here. So if I do that, I'm going to do 3 times 81. That gives me 243. Minus 1 is 242. Hey, what do you know? That worked. Okay, so we can see that the summation notation and the explicit formula I've written do actually work. Okay? So we've talked about this sigma and how it's the Greek letter used for a sum. Okay? Well, I'm going to talk about some other. It's all Greek to me. That's a phrase people will use sometimes when they don't understand it. It's all Greek to me. All right, well, here, let's talk about some Greek. You may have seen this symbol before, the I, the H, and the S, and some religious symbols. Here's a very old version of it. This is used a long time ago. This is a carving, okay, and an ancient religious, it's actually in some tombs, okay, and this is used on tombstones sometimes and things. So this is an ancient carving. It actually is the abbreviation for Jesus. Okay, these are the first 3 letters, the first 2 letters, and the last letter in spelling Jesus in Greek. I, H, and then S, sigma, the S, okay? So this is the Greek abbreviation, first 2 letters and last letter for Jesus. It used to be written as the IHS, and then it would have a line over it like this, indicating it was an abbreviation. Over time, that line over the IHS turned into a cross, a little more religious looking. So that used to be just a line over there indicating an abbreviation. Now it's turned into a cross. And then it was used a lot of times to indicate a host, right? Jesus himself. And so that kind of, sparkling starburst out from your glistening host, the Holy Spirit, the light of the Holy Spirit, turned into kind of a sun in flames around the IHS symbol with a cross. And oftentimes you'll see it with these 3 nails here, right, for the crucifixion, right, the 3 nails used to crucify Jesus. So IHS began as the abbreviation for Jesus, okay, first 2 letters and last letter in the Greek spelling of Jesus, and the other symbolism that goes with that. All right, let's get some more summation notation and series, all right? So we talked a little bit about up here. The explicit formula writing, that's what this is, an explicit formula. We wrote those in the last couple of problems. If it's a linear function, then this is arithmetic. So linear, right? We have like an mx plus b, right? This is this slope, if you will, right? That's our common difference, right? The slope is the common difference. We saw that in the other problems we've written. So this right here, this is linear, summation notation. So the explicit formula is linear, okay? That means this is going to be an arithmetic series. We don't have to even be told it's arithmetic. So we can use what we know about arithmetic series to find the sum. We could take 1 and plug it in, then take a 2 and plug it in, then take a 3 and so on, all the way up to 60 and add all those together. That is a lot more work than we need to go to. If we recall, okay, our summation notation and how we can turn that into a sum, we can use this for the formula for finding the sum of a series, right? So how many terms does this have? Well, it has 60 terms, right? We can see that right here, 60 terms. So we know the n. What's the first term? We are going to have to figure that out. What's the 60th term? We're going to have to figure that out. But those are the only 2 we're going to have to plug in. We don't have to plug in 2, 3, 4, 5, and so on. So let's find out a sub 1. So our n, as we know, is 60. A sub 1 is 3 times 1 plus 2, so that comes out to 5. A sub 60 is 3 times 60 plus 2, which is 182. So now we can take this and we can find sum of all 60 terms is 60 over 2 times 5 plus 182. And if you do those calculations correctly, you're going to get 5,610. Okay, 5,610. So we can use this as a very direct way to find the sum of something else without having to plug in all the numbers. Again, only if this is linear, so we know that it's arithmetic, right? This is our common difference. We have to have a common difference to know it's arithmetic. This only works for arithmetic series. All right? Let's see one more example here. And in this case, we don't have a linear equation. This is not linear. Okay, so we can't use that equation we had, S of n equals. So in this case, we're actually going to have to plug in a 1 and then a 2, up to 8. So we're going to have to do some calculations, and then we're going to figure out what the sum is by adding them all together. So first, we're going to find a sub 1. So a sub 1 is 1 minus 3 squared. A sub 2, 2 minus 3 squared. And so on. Again, we're plugging in n to our equation that we have. Right? We can plug in here. We can take numbers for n and plug them in. So we'll keep going. We'll have a sub 4. And that's 4 minus 3 squared. And we're going to go all the way up to 8. Right? Because we need to have the first 8 terms of this so we can add them all together. Right? A series is the sum of all of these numbers. And we're almost there. 8 minus 3 squared. Okay? So now we're going to figure out these. 1 minus 3 is 2, negative 2. Negative 2 squared is a positive 4. Okay, and so on. 0 squared is 0. So you should get these values when you do the calculations. Again, take here. 6 minus 3 is 3, and then we're going to square it. That's how we're getting the 9. Okay, and then 16 and 25. And now if we add all of these together, right, that's our sum. This right here is equal to the sum of all of those numbers, which comes out to 60. Since it's not arithmetic, we can't use that S of n equals n over 2 times the sum of the first and last terms. Okay, but we can still find the sum by getting all the different terms and then adding them together. Right? There's only 8 of them, so it wasn't too bad. If that was a 50, we wouldn't necessarily want to do that, and we're not going to do any that are that long of a series. We have to calculate each term. So when we see those where it's a long series of calculations that we'd have to do, right, we want to look for the more direct way when it's a linear and we have a common difference here that we can use and just find the first term, the last term, and use this equation to find the sum. So remember, a series is a sum of all the terms. There's some different things we can do with it, knowing the number of terms we have, the first term, the last term, and be able to come up with a sum if it's linear, being able to write out the summation notation. So understand the different parts of this notation and what it indicates.